Hi guys, in this video I'm diving into a reverse engineering tutorial of a ground control point base plate used with the Chair C1 LiDAR scanner. I'll be modeling this part in FreeCAD. It's pretty straightforward, so it makes a good beginner-friendly reverse engineering tutorial. The original part was die-cast and CNC milled. Since Chair 3D Cam doesn't sell it, we need to reverse engineer it and 3D print our own. You will also need a 1/4 inch threaded thumb screw. It's easy to find at most online stores. The one I've got here matches the thumb screw that comes with the original S20 base plate. The original one has a translucent cross marking, but honestly, I don't think that's necessary. I've been using the one that comes with the Trion S1 and it works perfectly fine without being translucent. The main thing is that the cross mark has to line up with the handlebar profile just like on the original base plate. I tested the ground control point accuracy of the C1 and the error was only about 6mm. In a future video, I will make a base plate that works with the Falcom F38 quick release. That way, you can slide the plate in and out easily while still mounting a scanner on a monopod for extra height. I'm kicking things off by 3D scanning this base plate with the Creality Sermoon X1. I'm scanning in 7-line laser mode at 0.2mm resolution. During the scans, I will try to capture as much of the side surface as possible, since I will use that later to align with the bottom scan. So I will do another scan for the bottom side. Since the Sermoon X1 is highly precise, it can align this thin parallel wall object with just 2 scans. For other scanners, you might need an extra bridge scan to help with the alignment. Next, I will fuse the point cloud at 0.2mm resolution. Then I will manually align the 2 scans. I will rotate both scans so they are in the same orientation. I'll pick 3 pairs of reference points along the curved side wall. They don't have to be exact. The software will fit them using the curve. And there we have it. The point cloud perfectly aligned from just 2 scans. This wasn't possible in earlier versions of the software, but Creality Scan has come a long way in the past 2 years. I will create a mesh with about 1.4 million faces. Now you can see the scan quality. It's tough to get anything better than this. Technically, you could go ahead and print this as it is, but it's not really suited for FDM printing. The hollow bottom face, the rubber feet, and missing cross mark make it less practical. I will export the scan as an ASC point cloud so I can align the planes in Cloud Compare. Next, I will drop the file into Cloud Compare, change its color, and use the 3-point alignment tool to align one of the bottom faces to the XY plane. The scan is upside down, so I will flip it 180 degrees along the y-axis. If you look at the point cloud from the X1, it's thin, noise-free, and crystal clear. This is what makes it feel like a truly professional 3D scanner. It speeds up and simplifies reverse engineering. Next, I'll save the file in PLY format. When prompted, I will choose ASCII and then it will be ready to open in FreeCAD. In FreeCAD, just select parametric body, go to File, Import, choose Point Cloud, and pick the file you downloaded from the video description. Click on the point cloud, pick a brighter color, and set the point size to 1. Click on the origin plane and turn on its visibility. Then select the XY plane and create a new sketch. I fine-tune the point cloud to sit exactly on the mirror plane. Create a 3-point arc around this circle, then measure its center from the origin. It reached 43 microns. Right-click on the point cloud, choose Transform, and in the U box, type 0.043 mm. Draw another 3-point arc on the larger hole. Measure its distance from the origin, and if it's too far off, rotate the point cloud along the W-axis until the distance narrows. Now the point cloud is only 14 microns away from the mirror axis. This is the right way to go when you are doing high precision reverse engineering. Now you can either turn off the alignment sketch or just delete it. Click on the XY plane, select Datam Plane from the top menu and slide it down along the Z-axis until it touches the bottom face. Click on the new Datam Plane, create a sketch, and now we can trace the bottom face of the base. Just draw straight lines along the sides, extending past the corner so they are easier to adjust. I draw a vertical line through the origin point. This will serve as the mirror axis. Next, use the block constraint to block all the straight lines. Then create a 3-point arc along the corners. Next, use the tangent constraint to connect the arcs with the straight lines. If you see the line isn't connected, use the coincide constraint to snap the point onto it. Next, carefully trim all the extended lines. Zoom in to check they are fully trimmed, and the connected point should turn orange. Next, select all the lines, choose the mirror command, and use the vertical line as the axis. You will need to delete the mirror line before running the Extrude command. Then close the sketch, select it, and choose Path. I set the extrude height to 8.1 mm. Next, I will click on the body and increase transparency so the point cloud is easier to see. Next, click on the top face. It will highlight when selected. Then create a new sketch right on it. Draw a vertical line through the origin point. This will be the mirror axis. Then trace straight lines along the inner wall. There are only 2 in this profile. Block constraint all the lines, then add 3-point arcs at each corner. Then use the trim command to cut away the line on the left half. Select the right half of the sketch and mirror it to the other side using the vertical line as the axis. Select all the lines and use the offset command. For FDM printing, I set the wall thickness to 2.6 mm. Next, click on the sketch and use the Path command to extrude it. Click the top face, then create a new sketch directly on that surface. I'm going to draw a circle, align its center to the y-axis, and use it to cut a hole for a 1/4 inch thumb screw. I set the hole diameter to 6.1 mm so I can tap threads into it. Click on the sketch and use the pocket command to cut the hole. Select the bottom face and start a new sketch on it. Right-click, choose External Projection, and project the hole for alignment. Create a circle with a 24 mm diameter. Use the pocket command to cut the circle until it reaches this point. If it's any thicker, the 1/4 inch thread may be too short. Click on the chamfer command, select the edge and set the chamfer to 2 mm. Then add cosmetic chamfers along these edges. Select the top face, create a new sketch, then draw a circle with its center aligned to the y-axis. Use the pocket command to cut it down 6.2 mm, leaving a 0.8 mm wall for the cross mark. If it's thicker, the mark will be harder to see. I also add a taper angle to the wall. I created a chamfer around the circle to make it look shallower. I went back to the bottom extrude cut, delete the projected circle, and add a taper angle to the cut. This makes tightening the thumb screw easier. Create a sketch on top face of the hole, project the circle, and draw a straight line. Then use the offset command to shift it by 0.5 mm. Use the alley command to make 2 copies of the profile and rotate them 180 degrees. Since FreeCAD doesn't let me do a full 360 polar alley, I had to create 2 copies at 180 degrees and another one at 90 degrees. Next, create a 5 mm circle and trim all the lines inside it. Select the sketch and use the pocket command to cut it through. And that's it. The reverse engineered model in FreeCAD is complete. To export the model, select the last executed feature and choose Export from the File menu. I will export it as both STL and STEP for comparison. I also want to try exporting in IFC format. IFC is a standard used in BIM and it can be opened in most major CAD software. I will test it in BricsCAD. Okay, exporting to IFC from FreeCAD didn't fully work. The circular geometry was converted into a rectangle. Okay, let me try to export as a step file from FreeCAD, and it seems to work fine. The geometry looks accurate. Step is a CAD file format, not a mesh. It has infinite resolution, small file size, and can be remodeled in other CAD software. See, I can cut holes, add fillet, or chamfers to the FreeCAD model directly in BricsCAD. Orca Slicer can read step files, but once imported, they are converted into a mesh. The advantage is you can control the resolution. This model ends up with about 17K faces. You can tweak the linear diffraction setting to increase or decrease the number of faces. When I import the STL file from FreeCAD, it only has about 6.6K faces, and you can see the lower resolution with a polygonal look. There might be a setting in FreeCAD that lets you export STL files with higher resolution. I'm going to use Kexel's K8 polycarbonate filament for printing with heat resistance up to 110 degrees Celsius. The base plate can safely rest on a concrete in the summer sun. But polycarbonate isn't easy to print. It needs a very hot build plate, and the surface often comes out glossy with tiny defects. So I will also print this with ABS carbon fiber. It's easier to work with, still heat resistant, and we will compare the result. Here's the polycarbonate print. It's glossy with some small surface defects. The top wall feels rough, but the fit is perfect. And here's my favorite, the ABS carbon fiber print. The layer lines are very visible. It has a matte look, and the surface quality is excellent. BQ sent me this filament for review last year, and I still have some left. ABS isn't as stiff as the polycarbonate. You need a flathead screwdriver to tap the 1/4-inch thread the first time. After that, it locks onto the base plate just like the original. And once installed, the thumb screw sits flush with the bottom face of the base plate. And when you place it on the marking, it's easy to see and read clearly. Alright, here's your 3D printed chassis 1 base plate. I dropped the link in the description. Thanks for watching.